Hello, welcome to Quantitative Neuroscience and Mathematical Method in Neuroscience. This is week 4. My name is Jiwan Myung at Taipei Medical University. Once again, if you have any questions, please send an email to jiwan@tmu.edu.tw. So let's move on to this week's lecture, which is about a simple T-cell model. As you know, T-cell is an immune cell, also called a lymphocyte. And T-cell has served as an ideal model that can be described with quite simple, easily accessible mathematics. Well, we're going to use the same mathematics that we have used for the epidemiology model, which is about how state A can change into state B. We call it compartment model. This is in general called a kinetic model. And the T cell is composed of many different parts, of course. It has a receptor and it has intracellular signaling pathway leading up to the gene expression. And after gene expression, there will be another screening process before any neurotransmitter or signaling molecules are being released. So a T cell, although this is not a neuronal cell, can serve as a very nice model to demonstrate how the phenomenon happening in the T cell can be modeled. Before moving on, we would like to think a little bit more about the previous talk, which is the epidemiological model. And once again, it has been called the compartment model. And we thought about 3 compartments. First compartment is a susceptible compartment, which is a population that are naive, not exposed to the virus yet. An infected population is the ones is composed of the ones that are affected by the virus, the infected. And then after some time, immune system, the body, will let us recover. So there will be a recovered people's compartment. So we have 3 compartments, and we are basically thinking about a scenario of one-way flow from the susceptible to infective to the recovered. So there's no coming back from recovered to susceptible. Once you acquired immunity, you are protected. You don't get infected again. So this is a one-way flow. But then we realized that although this is a one-way flow, well, this is quite simply one-way flow if you think about the flow from infective to the recovered, because the recovered will be proportional. The rate of the increase of the recovered compartment will be proportional to the infective population, multiplied by some kind of rate constant. So if you move back to the infective, you can simply take this value out, because this much will be moved to the recovered population. And there are incoming population to the infective compartment, which is proportional to ratio of susceptible population by the ratio of infected population over the total population. This is because we are making an argument based on the probability. Any of a susceptible component will acquire the virus only when it is in contact with the infected, just like this. So when they are together, when they make contact, then the virus will be transferred. So you have to think about the chance of those 2 compartments, components from these 2 compartments are meeting each other. That will be proportional to, once again, the ratio of susceptible multiplied by the ratio of infected. So we have all those arguments. And also, once again, if you think about the decrease of the susceptible population, it will be proportional to the same amount that moves to the infected. It's just that because the same amount will be decreased, there will be a minus sign right there. So this is a compartment model, and this kind of modeling can be applied to any kind of phenomenon, such as an intracellular dynamics, which is what we are discussing now. So for simplification, we don't think about the recovered population now. We only think about the susceptible to infective population, and of course this model is called SI model, because we think about only S and I. And once again, this is what I have already covered. When S and I meet an infected population per some change in time, which is the ratio R. So but then by the same amount, the susceptible population will decrease. So we just add a minus sign if you think about the rate of change of the susceptible population. So this is really the same thing. But although this model is quite simple, one important feature that we have to think about, which is that when we suppose that when S and I meet, and that's the condition for the susceptible to transform into the infective, we are supposing S is once again the ratio of susceptible over all population, and I is the ratio of infective over all population. That means any one of those person in the susceptible is able to meet the infective. So we are actually thinking of a case of all-to-all coupling. Each of us is able to meet an infective with equal probability. In reality, that is not true, because you need to have a logical proximity. You need to be nearby this person. But then in this model, we do not really think about these geometrical constrictions. So we meet with this probability of this ratio of S multiplied by ratio of I. And when this connection is made, this person will be affected, and this person will move forward to the infective compartment. Now, here's why we call this is exponential growth. Now we have two infected populations, and each one of them have a possibility of affecting the susceptible population with equal probability. So we have much more complex connections, and we have basically, doubling the chance of creating more infectives. And because of that, instead of just one person being infected per time, we will now have two people being infected per time, and then they will move to the infected population, and now 4 people will be affected by the same process. So this is just speeding up rapidly, which is called the exponential growth. So we do not increase the number of infective population with the same constant rate, but it actually changes over time. It actually increases each time, which is the reason why rapidly the whole population will become infected. Now we consider a case where we put this person who is infected to quarantine. So this person is isolated. When this person is isolated, this person is unable to make any connection to the susceptible population. So in that case, there will be no further transmission of the disease. So this is the best method that we have to control the spread of the disease. Once again, this has been the SI model. And we also consider the SIR model by considering recovery compartment. And now, in addition, we can also think about an SIS model. So the susceptible population becomes infected, But we can suppose that the acquired immunity doesn't last long. So after some time, the infected person may come back to the susceptible compartment without any immunity. It just means that the immunity doesn't last long, or the virus mutation in the virus is rapidly progressing, so it may affect the person who had previously attacked by the virus again. So the infected population can come back to susceptible. But in that case, simply because the infected population will spontaneously recover, this will be from the I compartment with the rate of B, for example. And by that amount from the infected compartment, this amount will be decreased. So we have a minus sign over here. And this is SIS model. So once again, because we are moving from S to I to S, it becomes SIS. In the same manner, you can think about many other compartments, some other scenarios, like some of the recovered population may come back to susceptible because they lose immunity, or their acquired immunity doesn't really work. There may be many reasons, and you can just expand the model in many different ways. And then once again, you can also think about some quarantine compartment, so that some of the infected population can move here without being able to affect the susceptible population. So model can expand in any way possible.